Morning, everybody. Welcome to lecture 18. We're going to pick back up with floating point. So just to recall, in order to get a number into binary representation, most systems you'll deal with will use one format. It's one that the IEEE developed. There's a newer version of it occasionally. The one the book talks about is from 1985, but it's otherwise known as IEEE 754. And then it may have a dash in a year after it. But 754 is enough. That's the name of the standard. And it requires that we normalize our floating point number and then split up the parts and store them in a binary word. So for MIP, since it's 32 bits, we've got a certain number of bits for the exponent and a bit for the sign. We don't have a bit for a decimal point. We don't have a bit for the leading one. Every binary number will start with a leading one if it's normalized. We don't make a space for that because we just remember to add it when we're done. It's there every single time, and so why waste space on something that never changes? We only want to use those bits to store the things that are different from one number to the next, like the exponent or the sign bit. And then the last part is the mantissa. That can change as well. All the rest of the bits that are not used for the sign or the exponent are used for the fractional part of the number known as the mantissa. So in general, this is the format that you always want to refer to. And here's the name of the standard again. There are two representations that our book covers. One of them will let you represent a number where the inputs are 32 bits each that require that we tack two registers together for that the answer could be more than 32 bits, and it's likely that it would be unless you're multiplying by 1 or 0. And double precision, which is twice of everything. There's even quad precision, and they can kind of get a little bit crazy and big. Here's roughly the layout. You start with the sign bit, then the exponents, and the fraction. Couple of confusing things. The sign bit does not refer to whether the exponent is positive or negative. It refers to whether the number as a whole is positive or negative. So in other words, it's a plus or minus 1 that goes in front of the imaginary 1. Always remember to put there. And the radix point, which is the technical name for a decimal point when you're not in decimal, and then the mantissa, or fractional part. And we're in base 2, 2 to the, and then this is where the exponent is. And if you remember, we used bias to take our number, which would be sometimes negative and sometimes positive. What we do is we map it into a representation of 0 to however many bits we have for the, and we basically are mapping all of our numbers over to here by adding something to them. So the negative number here has to have a bias added to it to turn it into 0. So if this is minus 127, then the bias is plus 127. And by adding that, you'll get to 0. Similarly, if this is a 5, then you're going to add 127. So this is going to be 132. And if your biggest number is, 120, 128, then this is going to be 255, so on, right? So we want to be able to represent negative numbers, but we don't want to mess around with a special format. So we just remember this bias, and this bias is constant for the size of exponent. So if you switch architectures and use a different size word, or you decide to use double precision floating point, then the number of bits you have available for your exponent will change, and therefore the bias will need to change. You need to move this up. So this is exactly the same size as this. They're exactly the same size. So if you give more bits to the exponent, then 2 to the n minus 1 is going to be wider, and then therefore you'll have more room here. You just need to shift it to the right. That's all we're doing. And then to come back out of the number, when I tell you what the binary bits are in an exponent field in a 754 number, in order to turn that back into something that you and I understand as regular decimal number, you can figure out what it is in decimal here. Let's say you look at the bits that are in the exponent and it's in decimal 100. I'm going to subtract 127 to go backwards, back down to where I was. And you can see already that when I do that, I'm going to be down here in negative land. So it's going to be 100 minus 127. So apparently my exponent in this case was minus 27. All right, so that's the trickiest part. There are really good simulators, and I'm going to show you one and drop it into the lecture folder as well. And let's see if I can find it just by, here we go, floating point converter. It's by schmidt.net. Yeah, hschmidt.net. And this is the gold standard. So I'm going to drag it into your folder for lecture 18. We talked about it last time as well, so I'm going to drag it into lecture 17 as well. And here's basically how this works. You can do it one of two ways. You can set the bits here that you find in your floating point number. Just set wherever they are, and it will tell you in decimal the representation is minus 642.5078. And trying to really represent this, and you can't always represent exactly a decimal number. Do you remember we had one we studied some lectures ago where we took a fairly simple decimal fraction, 0.5158, something like that, and we could not convert it into a finite number of binary bits because it's infinite series and binary. So what you're basically seeing here is that the value that's actually stored in float is smaller than that, but they're cutting that off for you here. And there are strange things that we're going to see today, so I'm going to leave this thing up. You can Google around for other tools to go in the other direction. I don't think this one will do it. I don't remember that it will. We can try. No, it does. Yeah, so you can just type in a number here as well. I thought, I'm probably misremembering. It seems too good to be true. So if you type in a decimal number here and hit return, it will show you the IEEE 754 representation of it. So this is exactly in the order that you need. There's a second row here of bits, and that's just because my window isn't quite wide enough. So if you spread your window out, then you'll get nicely in a row. All right, makes sense? Okay, so the missing one, the imaginary one, would be right here. And just to show you, I'm going to enter the number 1, and you'll notice there's no bits over here on the mantissa set whatsoever. The only thing you have is you've added 127 since it was times 2 to the 0, and sure enough, here is 127 in my exponent field. Okay, back over to the slides. We're getting just a little bit deeper into this, and we're going to take a look at some other interesting anomalies today. We talked about single and double precision. In double precision, your bias is going to be different than it is in single precision. So single precision, the bias is 127. It never changes. It's always 127 on any system. It's doing what is called single precision floating point, which at the time they developed this standard, single precision was meant on a 32-bit computer. So if you're dealing with a 32-bit word and you're trying to put a floating point number into it, then you're going to use minus 127 as your bias. So take the actual decimal exponent, subtract 127 going in the binary representation, and then add it when you're coming back out again. Double precision, it's 1023. It's one less than 1024. So 2 to the 10th minus 1. Floating point precision, relative precision, all the fraction bits are significant, even if there's zeros. So the single precision floating point number has a relative precision of about 2 to the minus 23rd, which means if you change from one binary number to the next binary number in the mantissa, you are incrementing by about 2 to the minus 23rd. Fairly finite, fairly granular precision. And if you have a very large exponents, then you're hopping, much greater distances as we talked about last time. So here's an example, minus 0.75. What is that? Well, first of all, we know the sign bit is going to be -1. So I'm going to follow along here on the side. So the sign bit, -1. And our rule was you take the sign bit, whatever it is, and let's go back up to our definition here. It's -1 to the sign bit. So we're going to take that. So in the case of sign bit, since it's a 1, then this equates out to -1 times, and then we have the imaginary antissapart, and then we have the fraction. Go back over to where we were. -1 to the 1 times, now what is 0.75? It's going to be very helpful to you, and you'll have this on the study guide and or the exam, to make a little table for yourself. Fractional values, and sorry it's a little bit crooked. I wouldn't live in this house if I were you. If it's 0.5, it's 2 to the -1. -2, 0.25. You want an eighth, then you're dealing with 2 to the -3. 2 to the +3 is eighth, so 2 to the -3 must be 1/8. Okay? And then 0.625 is 2 to the -4th, and so on. So back over in that site that we had, every time I click on one of these things, I'm going to an increasingly more negative power of 2. So this should be 0.5. This should be 0.25, 0.125, 0.625, and then you get down to the end, and it's crazy, right? All right, so if I need to do a number, back to my slides, of 0.75, how am I going to get there? Well, I'm going to focus on the decimal part alone. I'm not going to bother trying to figure out the part and the decimal part at the same time. But what I know is I'm going to use a combination of 0.5 and 0.25, because that's going to get me up to 0.75. All the problems I'm going to give you in the homework and on the exam are going to be combinations of the first batch of these negative powers of 2. I will not give you one that's 2 to the -23. Okay, it'll be 2 to the -1 through 2 to the -8, something like that. So you should be able to look at the table and quickly observe what it is you need to do. If I gave you 1905, I'm doing this correctly in my head, and you know this is too big, this is too big, this will fit, and this will fit. So it must be these two numbers added together, which I hope is what this is. That was my intention. And I look over here and I see it's a -3 and a -4. Therefore, the bits I'm going to click in that simulator, I'm going to leave the -1 alone, the -2 alone. I will X the -3, and I will X the -4. So my binary representation is the imaginary 1 plus 0, 0, 1. You see how that lines up? Right? So these are the two zeros, and these are the two ones. So in my case, I have 0.75. I observe that it is 2 to the -1 plus 2 to the -2. So I'm going to have these two guys checked off in this case. So it's basically 0.11 times 2 to the 0. Will get me exactly what I want, but that is not normalized, right? So I have to normalize this. So to normalize it, this is too small. This number doesn't start with the 1. I need to make it larger so that it starts with the 1. So I'm going to move the decimal point to the right, and I make it larger here. So I have to compensate for it by making it smaller over here, so that larger and smaller up to what it was before. So since I moved it right 1 decimal point, I'm going to move this down by 1. So my number now is actually right. We'll just need a different color. It's 1 plus 1. So this gives me 1 times 2 to the -1 times 2 to the -1, right? So when it comes time to write it down, I insist on making this 1 show up over here, because it's definitely part of the math, but it will not appear in the IEEE 754 representation. It's that leading one that's always there. So when I look at, in this case, what I really need to do It's in that tool that I need to click. It's 2 to the minus 1, minus 2, minus 3, and minus 4. I only need this one to correspond to that. I do not need, nor do I have a place to put it for this one, which is 2 to the minus 0, which is the one basically. That's assumed. So I have my sign bit, my mantissa. The only thing I'm missing is the exponent. And the exponent I want to represent is -1. So the rule is you take whatever exponent is you want to represent, you subtract 127 from it, and you're going to end up with 128. So in my 8-bit number, I'm going to have this bit clicked because this is 2 to the 7th. This is 2 to the 0. That equals 28. So let's see if I've pulled this off correctly. I'm going to clear this out, and we're going to leave the sign positive. We're going to there. Let's see, did I do this right? It's minus 128 though. So I did not do it right. This is true, it's plus 128, but I don't have a sign bit. Remember, don't have a sign bit for the exponent. So whereas this out here, sign bit that I have, remember, it's not for the exponent. So I leave this as 0 because it's maybe a positive number over here. What do I want to do for the exponent then? Well, here's where you can start to play around a little bit. What happens if you pick a number that's a little bit bigger than this? Something that's, look, down here, 126 minus 126 denormalized. Can I pull it off? Let's find out. -1 plus, so to go from the representation back out of the bias, what this one is basically saying is I take my exponent and I add the bias going in and subtract it going out. Now let's go back over and look at our diagram. Try to make every little to this that I can. I failed to follow this rule, right? So what I'm trying to do is shift it to the right. My number that I want right here, this is -1 in decimal. So if I just look visually at this diagram and I remember shifting, I know the number that I need to end up with needs to be a positive binary number. I don't have a negative sign. I don't have a sign bit. So if I shift this over, this was my halfway point here. So I should end up someplace just before that. So somewhere in the 130 range, something like that, give or take. So let's go and check it now in their math. What they did was they added 122nd and they got the 127 rather, and they got 126. So back over again to the tool where I can play with this all I want. I want to look at how do I get 126 out of this. This is positive 126 right here. And it is represented, this is the representation of your exponent bits if you're trying to communicate to me that you have a 2 to the -1 as part of your number that you're trying to represent. All right, I think I finally got that right. And then what about over here? I need the 0.5 and the 0.25, right? Well, but wait, this is getting me a different number. What I wanted to represent was -0.75. I still have lots of moves in this thing. First of all, I need to set the negative bit. All right, got that part done. So why is this the 5 and the 0.25 what I thought I needed to get 0.75? The problem is I forgot about the implied one. Remember the implied one over here doesn't actually go in the number. So shift all that to the left. The bit that's here will be imagined, and the bits that's here will be moved over one. So in other words, just unclick this. Finally, I have my number the way I'm supposed to do it. Okay, and in the MIPS commands, these have a series of commands called float, and they actually have different number representation formats. So if I want to pull this up in my green card, let's see if I can do that in here. can't remember if it was in, oh, it's in extras. There it is. We're old school at this now, right? So here's a bunch of floating point ones over here. The format sometimes is R, which is extremely handy. Sometimes it's I, which we can see here, it's handy too. And sometimes it's FI and FR. And here are those two new instruction formats down here that we see. This one looks a little bit different. They got rid of the shift amount. They moved a format field in here. They still have 3 register number operands, still have a function field, but they represent floating point numbers. So you do still have some mathematic ones here like divide unsigned, which are R-type, and they have 0 for the opcode and a 1B for the function code. What's different over here is they've given us a couple of other fields to represent something called format and FT, FMT and FT, in other words. These FI ones, which is the one, the FR and FI that we were just looking at, like here's an FR one, floating point add single precision. It looks just like regular old addition. FS plus FT equals FT, those are the register names. But here's what's really, going on in these numbers to let you know that that's what's happening. So there's another table that you could look at in Appendix A, Chapter 7 in the book, and we may get a chance to go through that a little later or in a different lecture possibly. Okay, so denormalizing numbers. If you, hey puppy, if you have numbers that are too small, then you're not going to be able to represent them in your floating point representation. And you also have some odd combinations of bits. So here's the deal. How do you communicate to a programmer that the result of a calculation is too small to be represented? You don't want to maybe just give them the number 0 because it isn't. And you can't represent what the number actually is. So one of the things that IEEE 754 proponents did not agree on was, how are we going to signal these special situations to the programmer? How are we going to let them know that I was able to do the calculation, but I can't represent the number? So the closest I can get is either a number that's too big, all zeros and a 1 at the end, or a number that's too small, which is actually 0. And it turns out there's lots and lots of examples like this of things that you need to communicate to someone, but which are super difficult to actually do. So to help us understand this, I think I have a handy dandy table. I think that was it there. And chapter 10, maybe. Let's see if I can get lucky and find it in here. There's a whole bunch of different number combinations that we would like to be able to let you as a programmer know are going on in your number. Now, you remember last time we talked about we've got flow as well as overflow, and we have this queue. And here's a nice little table that sort of shows you different sizes of the 754 formats. This is the one that we're using up here, 8 bits for exponent in a 32-bit representation. And then here is an extremely helpful table. So what I'm going to do for you guys is a bunch of these things out and keep a couple. And see if I need any of this stuff for you. Yeah, maybe. Maybe I shouldn't have deleted that. Let's store this in the folder for you because we're actually, this does not exist in any form or format in your textbook. This is not one of these where we have a little slightly different way of looking at it. Actually, just isn't there. So I'm going to drop it into lecture 18. Okay, and we'll pop it in here for you. So that's going to finish writing out. It's really slow, which is going to make me go insane. Okay, here we go. Now we're cooking. It's almost done. There's notes in these PowerPoints. One of the things that the author was good at and that I tried to add to whenever I could were some decent notes down here. So where we're at is basically at this table. And what this table is showing us is that certain kind of parameters, it shows us the largest and smallest numbers should all be exponents in here. They're shown as subscripts. They should be superscripts. We all know that with exponents. That's the case for this entire table. Never quite figured out sort of what that is. And what I want to get to in here are usual things in here as well. All right, so it starts off with kind of interval and rounding. So we had a discussion in a lecture a few weeks ago about how do you want to handle rounding. Here are the kind of 4 classes of rounding that lecture may offer to you. On Intel, you'll find there are options you can choose to select which type of rounding. The operating system may fix it for everyone, meaning by fixing it doesn't mean correcting it. It means setting it in concrete, not making it constant, the way that it's going to handle rounding, or it may allow you as a programmer to do it. But we had talked about that a little bit. We also talked about kind of interval arithmetic, and one way of controlling errors is to compute values above and below, and those are the 2 bounds that your actual number falls between. So there's a possible out right there. You remember the number we had that was too small? Maybe the way to communicate to the user is to use a routine that rounds down and then rounds up, and then compare the 2 numbers. If they're the same, then you got exactly the right answer. But if they're different, then it couldn't be represented, and one of them rounding up got you one number, and when you ran the equation again and rounded down, it got you a different number. Now you know your numbers in between the 2. So in our case, it would have been 0 for the lower number and all zeros and a 1, 0.0001 for the larger one. So that's a clever way of writing your code to just see if you've been given the actual result. So that's one way of letting the programmer know what's going on. The other way to do it is to just, okay, don't worry about rounding at all. Just chop things off. Well, that's the same thing as rounding towards 0, right? If all you ever do is throw off the bits you can't represent. How do you handle infinity? You've got every finite number between negative and positive infinity. How are we going to communicate to a programmer that the value that they've calculated essentially so big to be represented in the computer that it's the same as infinity? So an example would be 5 plus infinity, or 5 minus infinity, 5 times infinity, 5 divided by infinity, etc. So how do you want to handle these kinds of, how do you communicate to the user when all you have is a sign bit, exponent bits, and a mantissa, that something like this is going on? It's okay if that imaginary 1 stays in there if what you're trying to tell me is the answer is plus infinity, because I'll probably use that 1. But what if you're trying to tell me the answer is something different? That 1 doesn't belong. So here's what we've done. This is going to sound weird, but this works. We have classified these special cases into 2 categories. They're called essentially not a number, or NANs. And you can see NANs sometimes that show up in the strangest places. You may even see NANs on highway signs in Houston when they run a program to display, how many minutes does it take to get to the Shakespeare Festival or whatever, and they mess up the math. Let me see if I can find. I've taken pictures of these things before, but I don't know if I've got them organized in the right in the right spot. I'll find some. It'll come to me where I name them. But you can actually see them all the time if you look for it. It's typically spelled like this. So one of the things a programmer can do is actually print out, hey, this is a not a number. And if they can figure out that's what the CPU is trying to communicate to them, then they can write a line of code in C that says if you get this combination, then tell the user by just printing it out in English. This is a NAN example. And you'll see that programmers have indeed done that because you'll find them on displays and menu boards at McDonald's and highway signs, signs at the TDECU stadium. I've seen them in all those places. Just got to keep your eyes open for it. What a not a number is a um, something that's like one of the examples we talked about. 0 times infinity, 0 divided by 0, x remainder 0, infinity remainder 0, square root where x is less than 0, etc. So it's a symbolic entity. So what do you want to do to represent this to users? What we do in MIPS and what IEEE 754 does is they set aside special combinations of sign, exponent, and mantissa and take them away from you, represent an actual number. Perfectly legitimate combinations of those bits. It's just a sign, exponent, and mantissa. And so what we're doing is we're going to tell you, I know it looks like you have 2 to the 32 combinations of these bits, but I'm going to take some of them out of commission. I'm going to write them down in a table, and I'm going to reserve them to represent not a number. So reserved IEEE 754 combinations. Let's see if I can get lucky and find it this way with the wiki article. Um, Here we go. I want NAN. There we go. Let's see if they show us the representation here. If I get lucky with the table. Okay, bingo. So some representations. These are special combinations of numbers that we use to communicate to you. So when you write a math program like Excel, or you're writing your own code to calculate something, you actually have to build a big table to look for every one of these combinations and do something different. Don't just blindly calculate it and pass it along like you do all others. You actually want to look for these particular combinations. So for example, if somebody gives me a sign bit of 0, and they give me 128 as the exponent, and for the fraction field, they give me all zeros, what supposed to represent? It's basically 1 times 2 to the biggest number I can get. So if you see that, actually the biggest number you can represent, would be a 128 for the exponent, all ones for the mantissa. But that's not the one we're reserving for this. What we're reserving is the biggest possible exponent and all zeros for the mantissa. You should interpret that as a positive infinity. If you want to communicate negative infinity, set the sign to negative. Here's another one here. Set the largest possible exponent and then anything other than all zeros, including all ones. Those should all be considered not a number. So basically, we're taking away your ability to ever use 128 as an exponent. It's actually not possible. So the largest normalized number you can have is actually 2 to the 127th, and basically all ones for the fraction field. That extra 1 into the exponent field. So I'm going to drop this into the folder for you. See if I can actually get to, see if there's a spot up here that says examples. It'll I'll change the URL a little bit, so it should take you straight to this table. And I'm going to drag it into the folder for you there. All right. So there's 7/54/1985. Okay. Meanwhile, back at the ranch, look at some NADA numbers, some exponents, and they basically just give you a tiny little table of it, but the Wikipedia table is better. There's better ones even out there than that, but that one, everybody thinks of going to Wikipedia first, so I'm going to give you that page. If you need to add numbers together, if you have a 4-digit decimal example, like 9.999 plus 1.610, and the signs are different, what you have to do is align the decimal points, right? You know this. We've done this our whole math lives. So if I write these out, 99.99, that's what this first number is. And the other one is 0.1610. Sorry about the giant decimal point. I've aligned these things to add them together. So I'll do this, 100.1510. What I had to do here to my decimal points was align them. And the rule of thumb that we're going to use is to always shift the number around that has the smaller exponent of the two. In other words, make it match the big one. So if I go back to what I had before, and I had 1.610 times 10 to the minus 1, then what I'm going to instead do is make this number smaller by 2 decimal points, and in return, make that -1 that I had as my exponent bigger. So I'm going to have 0.001610 now, and then here's where I had my -1 plus 2 so that I match. Now I can add these together, and in my case of a 4-digit example, these get truncated off. So I've got to decide, what I want to do with them. Maybe I can keep a 4-digit one here. Doesn't create a problem. This is a round down. But if it's this one, maybe I round up to 0.002. So you'll have to just deal with however many decimal points of precision you've been asked to represent, and that's how you'll do it. Then once you have the alignment of the exponents accomplished, now you just add the significans together. You will normalize the result. So in my case, what I got was 10.015, and these were considered unable to be represented. So 10.015 and times 10 to the 1, which is what I had up here. Now I need to normalize it. Normalizing it is going to go 1.015. So I had to make the number smaller. So I need to compensate by making the number bigger. Right, so normalizing it's not going to get you into trouble. Fractional part there could cause you an issues. You may have to truncate, so you may have to round when you're doing it. Rounding could cause your number to go up. Rounding up could push this number out of range. You could have been very close to the maximum number representable, and by rounding up, which you do when you normalize and have to truncate this off, that can blow you out of the water. So you have to check for that. The other thing you have to check for is when you normalize, when you increment the exponent, this can now be out of bounds as well. If it's 128 or larger, you can't represent it. And so both of those things are issues. So once you normalize it, you'll round it and see what happens. Okay, so now if we take a look at a little more complicated example, and this time we're going to do it in binary. So let me clear this off, and we'll try doing one this way. So in binary, it's what they gave us was 1.000 times 2 to the minus 1. Wanted us to add to that a negative 1.110 times 2 to the minus 2. So we need to adjust the smaller one. So I want to push this to a larger thing. Therefore, I want to shrink this to a smaller one. So doing that would be times 2 to the minus 1. Now the exponents match. So now I can add these things together, add the significance together. And what I'm going to get is 0.001, because I took almost all of it away, times 2 to the minus 1. That's my answer. Now I need to normalize it. In order to normalize it, I need to have a 1 to the left of the radix point. That's going to require increasing the magnitude of this number by multiplying it by 2 to the third. And I'm going to compensate for it here, subtracting 3. And I will go back and write my number. There I have. This did not result in overflow or underflow. I was able to present it fine. No rounding is really necessary, and the exponent is within range, so I'm done. So what is this number? Well, if we go back to our table again that we had earlier, this time I'm going to write the table down a little bit differently. Not like that, I'm not. To the n, and n is minus 1, minus 2, minus 3, minus 4, minus 5. This would be a 0.5, 0.25 in decimal, 25, 0.0625, 0.03125. Okay, so this was times 2 to the minus 4. So this is basically 1, see, 1, 2, 3, 4. So 0, 0, 0 point. All right, so 2 to the minus 4, so 0.0625. I can draw it out if I want, or I can just go based on this and go straight to my table. So that, in fact, is the answer. If we want to go back up to the front and check, 1 times 2 to the minus 1 is 0.5 minus 0.111. 0.111 is 0.5 plus 0.25 plus 0.125, which is 0.875. So I think it's 0.4375. Well, it depends on if I'm, yeah. So it depends on if I'm doing this one or if I'm doing this one, and I'm going to shift it over when I'm done. But I'll do it every time just in decimal. It's not that hard. And then at the end, I look at what I've got, and I'll try to look it up in this table and just figure out what combination of ones it is. You can go over to the simulator and do it as well, which is probably safer and faster. Okay, so how do we do the hardware in order to do this? It's worse than just doing integer adds. And we also can't really get it done in a single clock cycle. So we usually build a separate adder for floating point, and it will usually take several cycles. But the good news is when we have passed through the first set of gates with one number and it's on to the second set of gates, the first set of gates are available for the next number. So when we do that, it's called pipelining. It's just like a laundromat in a college town. You can put things in the washer, then you move them to the dryer. Now the washer's free for the next person. And then when you move from the dryer to the folding table, they move to the dryer, somebody else moves to the washer. So you're pipelining these things through, stopping off. It's kind of like an assembly line. So the floating point adder, hang with me because you will follow this, right? So what we basically, and I think what I'm actually going to do is copy this over so we can draw on it a little bit. But I promise you this is not that hard. Be an electrical engineer to understand this. You might have thought you did, but you don't. So I have two numbers. Number one, my first number, my second number. I'm going to first take a look at the exponents for each of these and figure out which one's the smaller of the two. I subtract them and see whether the result is positive or negative. And the one that, if it's negative, then I know this one was bigger. If it's positive, then I know the first one was bigger. Whichever the smaller one is, I will take this difference that I just calculated it and add it to the smaller exponent. So this is going to be fed both exponents. I will calculate the difference. I will tell the control circuit, which is the brains of the outfit, look, here's what I figured out of the exponent. It's going to see whether it's positive or negative. It will take a copy of the exponent, which is sent this direction, as you can see, and the other one as well. And let me erase a little bit so I can switch my drawing tool to something that's yellow. See, not only did I get a copy of the exponents here, but I also managed to grab a copy of the exponents that also got sent along. Here, probably could have made that a little more orange and recognizable. Here and here. So once I know the smallest one, my difference, the control looks to see whether it's positive or negative, says which one of these to move on. So it's going to select, this is a multiplexer, it's going to select how to pass through here, the exponent from the first number or the exponent from the second number. And it's going to make that decision based on which one was the smaller one of the two. So it takes the difference that it calculated, it sends the exponent that needs to be added in here, increments it or decrements it. In our case, it's going to be incrementing it to make the two things match. And it's also going to take the fraction that I've got, because once I know the exponent that's the bigger or the smaller one, what I really want to do with that is use it, shift the mantissa left or right accordingly. Right? So if my right number was needed to have its exponent increase, then that means I shift the number around. So I'm also going to take, once the control knows what's going on with the exponent, it's also going to tell this pair of multiplexers sort of what's going on. It's going to add the mantissas together, of addition, but before it can add the mantissas together, it's got to make a decision about which one needed to be shifted. So multiplexer will only let through one that needed to be shifted. If it was this number, then it will allow that to pass through. If it was this number available to this multiplexer, this control signal will allow it to pass through. Get shifted. Whichever the smaller one was, whoever had the smaller exponent, theirs gets shifted to the left and made into a bigger number, and then they're added together. So now I have my addition done. I will send my result out. The result will look to see whether it needs to be normalized or not. And as I normalize, it could result in me needing to increment or decrement my exponent, which I will do again. I may need to round my result. I'm going to be taking a look at what's going on after I do that rounding. The control signal, take a look at it and make sure I haven't resulted in overflow or underflow or an exponent that I represent. If everybody's happy with this thing, then I will the exponent out. Again, the exponent is going to go, back up here and have another look thanks to the control circuitry. So this is where the checking happens. And what pops out the bottom, mercifully, after an eon, an eternity, is my sign, my exponent, and my fraction. It's possible when you do the shift left or right that your sign changes. That's why I don't just copy the sign, straight down here. I can't. I don't know what the sign of the result is. Right? So you may not understand this in total detail, but you can basically see we compare the exponents, we shift the smaller number right, we add them together, we normalize, and we round. So that's basically what's going on. It's a doable task to have to design something to figure this out. You could write the code to what the other chapter showed us. You want to go and look further. I think it was in this one. May not have been in this one. May have actually been in ours. Maybe lying about this. I don't see it. I saw it right before class, but I pulled it up in something. Maybe it'll come up next time. There was a giant flow chart that these questions. Is the exponent on the left smaller, bigger, etc.? I need to track it down. That'll help some of you. Multiplication's a little different. We don't have to shift things around. For biased exponents, you're going to take the bias from the sum of the two. You don't take the bias out twice. So if you've got 10 to the 10th and 10 to the minus 5th, as we do in this first line of our example, then I'm going to, when I multiply these things, basically add them together. So I'm going to end up with a 10 minus 5 equals 5, and that is my new exponent. Then I'm going to multiply the significans, 1.110 times 9.200. I'm going to end up with my number there, times 10 to the 5th. I once again need to normalize, check for overflow and underflow, and round if I need to. Check the sign. This time the sign is calculated differently. I determine the sign by inspecting the signs of the input operands. If they're both positive, the answer is positive. If they're both negative, the answer is positive. If it's one positive and one negative, then the answer is negative. So that's just a rule that I have to look up. If we do it with binary, it's very similar. I'm just going to add these two exponents together. Result will be times 2 to the minus third. And in bias, this is where you have to really be careful. I have -1. That biased format, when I stick it into the presentation, was 128. And when I had my -2, that's going to, sorry, that'll be 126, right? And this will be 125. So I'm going to have a -3 for these. So far, that part's good. I'm going to have the 127 in there twice. That part's not good. I don't want to do that twice. So I'm going to take one of them back out again to keep from completely screwing this up. The answer code to implement this, that's an easy way to get. All right, so that's kind of a really important part of this slide. And then you multiply the significans and you test the results. The floating point math hardware is for multiplication is similar to the adder, but that hardware is usually tasked to do all kinds of stuff like reciprocals and square roots and multiplication and division, addition, subtraction, all done with that operation, that floating point hardware, and it's one of your longer, slower instructions. Okay, so floating point instructions and MIPS have special registers. We talked about our special instructions. We took a peek at some of those things. Here are some of those L commands that they're talking about, but you also have load and store instructions that are popular as well, special ones for that as so. And you have single and double precision calculations in here as well. So let's take a quick look to kind of wrap this little piece up of how to convert from Fahrenheit to centigrade. So my C code, I'm going to call it F to C for floating point to centigrade. I'm going to pass in a Fahrenheit, of which I unfortunately chose to spell with the first four letters of the German word, which I don't know that many people would sort of recognize that instantly as being Fahrenheit. So what I want to return back is 5/9 times the Fahrenheit degree times the number minus 32. So let's just check. 2 is the freezing point of water. In centigrade, that's a 0. So 32 minus 32 gives me 0. This will give me 0. Great. What about the boiling point of water? 12 degrees Fahrenheit, 100 centigrade. 12 minus 32 gives me 180. 5/9 times 180, 5/9 gives me 100. Right? So my MIPS code is going to look like this. I'm going to load a constant from the stack. I'll load that in there. Let constant 9 and constant 5 past my GP pointer. So what this basically is saying is I'm going to go this number of things past the start of a pointer, and this one is a variable that represents going 5 things past. This is a variable that I chose to represent making going 9 things past a starting point and a global pointer. But what I actually have stored in those locations is the floating point number 5 and the floating point number 9. But those are so common that the routine that you see somebody here using is to refer to those with this phrase CONST5, 9, and then later 32. So this programmer is taking advantage of the fact that they've preloaded a whole bunch of constant numbers that they might need in a place past the start of a global pointer. So they've pre-stored a bunch of integers in there in floating point format. So I'm going to load those. Then I'm going to do my division between the two things. And I'm going to subtract the 32 floating point number from F18, and which was, let me see if I can figure out what they did here. I think they're reusing this twice. I have my doubts about this code, but we're going to continue on. Then I'll subtract that thing from it and then multiply by 5/9, and then jump back to the return address. So how did I get my result back? Well, hopefully what I did was put it in a that no one's going to touch, an invocation to the next. But what I don't see in here is any saving of registers that somebody else might have been using. I don't see using a V return register, etc. So things are a little different in the floating point world. All right, so we would have to study that more, or I be able to turn you loose with a bunch of coding exercises for something like that, and we're not gonna get that far. All right, so be thankful. All right, array multiplication. I've got double precision X's, Y's, and Z's, and I'm going to step through these things. Basically, these are all 32 by 32 matrices, but each of them is a 64-bit double precision element. That's unusual. So what I want to do is for K, I'm going to go through my Kth items, Xij, Yik, multiply by Zkj, and my MIPS code looks something like this. I have my inner loop here, I have my two outer loops around here as well. I have to continue down and look at what's going on in each of these. I have my branches to get back up to the loops here. This will branch me back up to the inner loop. And then once I fall out of that, I'll do this and set F4 equal to that value. And basically I'm adding as I go up. The guts of the matter is right here. Here's where I do the multiplication and the addition. All right, the add-on sign that you see here are just to increment the loop counters. That's all that's for. So the heart of the operation is right in here. So how accurate can we get? You do have rounding control that is specified. We've talked about that. You have a choice of rounding modes. You can fine-tune your behavior that way. You also can have what's called extra bits of precision that are built into the system that you don't normally get to see, but which an IEEE implementation can use to keep track of some extra bits so that when it's time to finish the calculation, you haven't done any intermediate rounding, intermediate values that would really affect your number. So let me give you an example of that. That's a little esoteric. Suppose I needed you to add some numbers together, like 0.01, 0.05, and 0.03. Ask you, let's put another 0.01 in here, and ask you how much money do I have? You might say you have a dime. But what if in fact the real values were 0.014, 0.054, 34, and 0.014? What does this add up to? Right, so this is going to be 5, 6, 7, 8, 9, 10, 11 cents. And then if the bank is willing to round up for you again, it's an extra penny. Well, that depends on whether you owe them money or they owe you money, doesn't it? So it's certainly not a dime. So that's an issue. What happened? What happened here is because we were dealing with dollars and cents, you did all of your rounding as you went along. You did your intermediate rounding here and you truncated off all of these values and you ruined your result. So if in my computer, if I protect some extra hidden bits from you over here, enough to store these kinds of things, then I can do my intermediate calculations and do the rounding once as it should be done at the very end, not each step along the way. Because not only did I get a different result, but I would even get another one even still, depending on the rounding mode that I chose. So those can be called guard bits or rounding bits or sticky bits or extra bits, however you want to refer to them. Good implementations will implement things like that. Okay, in graphics, we talked about the character in a video game model who's in front of a light source and the light source changes intensity, or maybe the character just moves closer to it or further away from it. Lots of recalculations have to be done for every pixel on the visible surface on the character that's facing you. Presumably there's pixels behind the dark side of the character. So how are you going to do that? Well, math for it is similar. It's going to be repeated many times. And you want to do the same calculation for each pixel. One of the tricks that we can use when we architect these systems is to allow that string of calculations to happen on each of those pixels in much of a parallel fashion as possible. So there are architectures that will allow you to a whole range of strings of data. Maybe you line them up in a special set of 32 registers and you put a math command in and you tell the system, run this math command on all 32 of those registers and put the intermediate result back in those registers again. And then I'm going to give you a different command and I want you to do that to all of the 32 numbers. They don't have anything to do with each other. You're not adding the registers together, but you're performing the same instruction and you only had to give the instruction one time and the system just iterated or did them in parallel, however you want to think about that. So that is a type of parallelism as well, called subword parallelism. It's also called data level parallelism because you're doing things on different pieces of data in parallel. You're not actually running different instructions. It's the same instruction on all of them. It's also vector type or SIMD parallelism. With Intel, you actually have the ability to do that. They have 8 registers that are very large registers, extended precision registers, and they use them as a little stack. So you kind of push things down the stack. This is similar to the stack that we've studied before. And they have this special set of names. You can put 8 numbers there and then run the same math on all 8 of them. There's commands set aside to do that. And yes, that's enough to really speed things up, believe it or not. It sounds like quirky. Why would that be any faster than doing them one at a time? And it's because you only have to interpret a single instruction. You only have to fetch one instruction. You only have to decode it. You only have to send control signals to the ALUs and other system components once. But because you're doing it in a special place, the system knows what to do. It'll just cycle through them quickly. So here's an example of some of the x86 instructions. And again, 86 refers to the last 2 numbers of a family of Intel CPUs, 8086, 8186, 8286. They got away from those numbers, but the set of assembly language commands, collectively known as an instruction set architecture or ISA, has grown, but it's never gone away. So even today, with the Intel chips that we put into laptops, they're still part of that same x86 family. They call them Xeons or Pentiums before that, et cetera, but it's all the same family of instructions. They've added to it, but the ideas are still there and the old commands are still there. They also have in Intel some streaming extensions where you can point it to an endless set of data, like data as it's coming in off of a microphone or a video camera, something like that, and it will just process those things through continuously and then place them into memory where another part of your program, wants them. So you may be writing Skype and you may want to constantly be taking input from audio, performing the same compression on all of it, and have it drop it into a location in main memory, and your job will be to grab a handful of those at a time and put them on the internet to send it to the other end of the connection, just like this code is doing with my voice, right now. So lots of clever ways of getting those things done. I have to figure out here how much of this matrix multiply we want. I think it's worth taking a look at some of these commands because Intel has some very clever multiply commands that are massively helpful to AV programmers, people doing things with audio and video, but it's a good stopping point for now. So even though we're almost done with the chapter, we'll just come back to the last little bit of this next time. All right, thanks guys. It's been a pleasure. Hope you have a great weekend, and I will see you back in class on Monday, Tuesday.